Good morning. So, we now go to the final part of our series of lectures on determinants, which gives a structural interpretation for a determinant. And that was our objective. So, once again, we have Rn. On Rn, we are looking at what are called n-linear forms, which we have discussed in detail, and we have also said that an n-linear form, if f is an n-linear form, on Rn, then f can be written as summation over phi belonging to Fn of f for E sigma of E phi 1, or let me write it this way, phi where E phi we have defined last time. This is the n tuple that's it. So this is the n tuple E phi 1, E phi 2, etc. E phi 1 where EI or E1, E2, etc. En is the ordered basis for Rn. Okay. So that is well defined. So also E phi tilde is E phi tilde, we have defined last time. This is equal to E phi 1 and we have E phi tilde of E psi equal to delta x. That means when phi equal to psi, this is equal to 1, 1 whenever phi equal to psi equal to 0, phi is not equal to psi. Now phi psi of course belonging to F. So these are the notations that we have introduced. Now I think everything is clear. Now let us start with the definition of alternating and linear. Okay. So this is the result that we have proved, which is a representation theorem for F in terms of E phi tilde. Now we consider an n-linear form with the property of being symmetric, being skew symmetric. Symmetric. Defined by, or I can, yeah. Now this is defined in the following way. That is, A is an nonlinear form A is said to be skew symmetric if A of x this is equal to signum sigma A of x1, x2, etc. This is for all A belonging to. Yeah. This means that if you interchange any pair of arguments of A, it changes sign. And you know that all permutations can be on n symbols can be classified into odd permutations and even permutations. Now, an odd permutation is something which can be written as a product of odd transpositions, and an even permutation is a product of even transformations. Even transpositions, I am sorry, it's not transformation, it is transposition. A transposition means interchange of two of the arguments, okay, or two of the symbols, right. So what you have is that, and we have also exclusively looked at these the permutations in detail, and there we have also said the following. That means if any permutation is written as a product of odd number of transpositions, then in any other representation for it as a product of transpositions would contain only odd number of transpositions. Likewise for even permutations. So that allows the classification of these permutations into odd permutations and even permutations. And consequently, this is what we get. You can link everything with A, x1, x2, etc. xn, where sign of sigma, st and sigma is equal to -1 +1 whenever sigma is even, and this is equal to -1 whenever sigma is odd. And this is a beautiful classification that is available on permutations. Okay. So this we are going to make use of. And one consequence of this is that if A of x1, x2, etc., xn, if A of is a skew symmetric and linear form. Then A equal to 0 whenever two of its arguments P, that is whenever xi equal to xj, I not equal to j, for some I and j belonging to this is because if you just interchange those that xi and xj, because the A is alternating, its value should be minus of A, x1, x2, etc. And but it is indistinguishable when xi is equal to xj. You know this interchange is not is indistinguishable, and the consequence is that A of x1, x2, etc. xn is 0. So that is simple. That we have. So that is something. So that essentially tells you that consequently A of x sigma 1 or x phi 1 x phi n equal to 0 for every phi belonging to Fn, such that phi is not 1 to 1. Because when phi is not 1 to 1, you see that some I is going to be equal to j, okay? Or some sigma I is going to, or some phi I is going to be equal to phi j for I different from j. Therefore, the consequence is that this is equal to 0. Therefore, so in this representation, some simplification takes place. What happens is that we get the following. Therefore, what happens is in one, that is the expression that is written here, if f is an alternating n linear form, you get several terms 0. Okay, so I just make statement about it, and you see that this is going to be hence what you have is that f A is equal to sigma n f all these f e phi's would be 0 for phi not 1 to 1. Okay, therefore only the terms involving the permutations would survive and all other terms would be. So this is the expression that for alternating nlinear. So that's a simplification that we. Now we will be working with this. Okay, so let me just take out this. A further simplification is possible of this using the property that A of x sigma 1, x sigma 2, etc. x sigma n equal to SGN A x1, x2, etc. Now you see this, if I write elaborately or detail, if I write this, this is A equal to sigma sigma is a permutation, and I'm sorry, I think I should write it A. So A of is square now you observe that using this property, using star, what you have here is you have A equal to A of E1, E2, En to summation over sigma, sine of sigma, this way. Okay, so I can rewrite the whole thing as using our notation. This is equal to A e pi where pi is the identity permutation. So we write it. Now, so that means pi I equal to what we have is pi I equal to I for every I. So use that convenient notation. It's not a universal standard notation or anything, but I have just introduced it. That's why I have mentioned it there. So what you have is this. Therefore, we have now this expression. So this is the representation for alternating for sigma becoming here. So that representation theorem is now. Now we make some observations. Now, one observation that we make is that E being A being non-trivial, A of E pi okay, A being non-trivial, A is not equal to 0 and linear. A is not the 0, or I will put it this way, A is not. That is A of E pi A of so that is clear. And therefore, further, the set of all alternating n linear forms on Rn forms a subspace of the vector space of all n linear forms on now what is special about this is that you have this subspace is one dimension and spanned by the alternating form sigma over So this actually spans. That means every such linear form is a scalar multiplet. Now this is in fact it is very precise here what that scalar is. It is the evaluation of A on E pi. And this is you can easily show that this is an alternating linear form. Alternating essentially means it's a skew symmetric linear. So it's a one-dimensional subspace of the whole thing. So any other alternating and linear form is a scalar multiplet. Okay. So now let us give or proceed to explore the interpretation of a determinant. Okay. Let A be a linear transformation on this. Now let us define an nlinear form in the following. Define an nlinear form by B of equal to A of clearly it's an nlinear because A is linear and A is linear in each of the capital A is linear and small a is linear in each of its arguments. When others are held fixed, you see that A is a nlinear form. Furthermore, because A is alternating, we have B alternating. Okay. That is because you can write this as y1, y2, etc. yn, ax1 as y1, ax2 as y2, etc. axn as yn. Now you see that because one can easily check this B of where y sigma I A of x. Okay. Now it is alternating, therefore it makes B also alternating. Okay. Right? So now it is easy to verify that this B is alternate. Now let us work on the following. So let us calculate this. So B of E sigma, this is equal to A of this is A of this, where sigma is a permutation of on N6. This is true for every N. Now what is the consequence? The consequence is that you have B by our structural result B of E sigma to B E pi B E pi sigma N sorry, okay, I should simply write here E equal to okay. Now let us work on B E pi. What is B E pi? We write down what B E pi is and then use the representation of A. So let us take B E pi this is equal to B of N is equal to A of A. Now we observe that see EI is equal to R. So let us write down this. So AEI is a linear combination of E1, E2, etc. En. Therefore, we have AEI is equal to, so let it's a linear combination of E1, E2, N with alpha 1I E1 plus alpha 2I E2 plus etc. plus alpha Ni E for I equal to and this is the representation that you have for A. Now, where of course alpha ij belongs to R, uniquely determined for I j belonging to, these are uniquely determined real numbers. Now, therefore, we will observe that, so if you were to write the matrix representation for A, the matrix representation for A based on, now this here I put E pi here, based on the ordered basis, and write it this way. This is equal to the following matrix, namely alpha 1 1, alpha 1 2, alpha 1 n, alpha 2 1, alpha 2 2, alpha 2 n. Alpha n. This is the matrix representation for A with respect to the ordered basis U1, E2, etc. Now we shall write this as follows. So B of E pi, this is equal to A of, let us write down this expression. So this is equal to summation over j alpha j1 ej summation over a alpha j2 ej alpha summation over alpha jn of ej. That I have simply used this expression. This is AE1, AE. Okay. Now this let me expand because I am now going to use the n linearity of it. Then I have the following. Then of course I have the n linearity of A. If I use that, this is what I get. This is equal to summation over tau the product of alpha tau 1 1 alpha tau 2 2 etc. Alpha tau n. This is something I think we should work out. Multiplied by a e tau. Now this is the product that comes out, and you have sigma, summation over sigma. Okay, so this is just expanding this. Okay, right? If you are in doubt, what you should do is take the case for n equal to 2 and use the follow the same symbol and try to find out what exactly you end up with. Okay, so this is equal to, you can very compactly write this as because I am now writing a tau, a e tau as signum a e pi multiplied by okay, let me write this. Now a e tau equal signum tau so we now make use of this. To make use of this, you get B equal to B pi sigma summation over sigma E sigma. This is just the definition. Okay. Now this you can write. Now we are going to write B pi, B E pi. Sorry, not B pi, B E pi. B E pi. Now we are going to write. Now this is equal to summation over tau alpha tau 1 into alpha tau 2 into etc. alpha tau n multiplied by a e tau so this is what one is. Okay, and that's equal to, you can rewrite in this form, summation over multiplied by sine of tau into a e pi into again this in the bracket and write e pi here, close the bracket there, and then write summation over sigma STN this is what I have. It's a simple repetition of whatever we did at this result we have applied. Okay. Now what does this give you? This gives you, now you see I can take this e pi there and then this part I can, so a e pi is common. So I can write this as a e pi all products into so I can bring this a e pi here. So they do come. So what do I have? I have this as sigma for tau alpha tau n. So the summation of the whole thing. So this I put in a single bracket. Okay, multiplied by a pi into summation over sigma. These are all permutations. Tau and pi are permutations. But what is this? This is essentially the determinant of flow. determinant of A into this is A. This part is A and this is the determinant of A. Okay. So what one gets is the following. So we get the following result. B is essentially equal to determinant of A times, you see the relation between B and A. See, B of or B of this is equal to A of AX1. This is something that you recall. Okay. This is for every okay. Therefore, let me, so that structurally defines what the determinant of A is. Okay. So this is the final relationship. The determinant of a linear transformation or a linear operator is not a something that you define in a very complicated way, but it has some structural meaning. The structural meaning is that the alternating a linear form B obtained from A by replacing each of the argument by A, x1, A, x2, etc., A, xn is again an alternating n linear form, and that alternating linear n linear form is given by, as I said, see, A serves as a single alternating n linear form in the one dimensional space of n linear forms. Therefore, every alternating n linear form is a multiple of the alternating n linear form because it's a one dimensional space. And what is the multiplying factor? That multiplying factor turns out to be. Okay. Now to justify the, because we have worked with E1, E2, etc., En. Now you can just note this also to see that B of AXN, therefore you have xi equal to psi I1 E1 because each xi is an element of Ri. So it's a linear combination of E1, E2, etc. En. Psi i's are uniquely determined. Psi ij's are uniquely determined. Therefore, AXI by linearity, this is equal to. Now, therefore, now we use the n linearity of B. So, B of x1, x2, etc. xn then turns out to be the following, that is summation over sigma. Sigma is a permutation psi p of and therefore this can be rewritten as summation over sigma I'm justifying this step essentially. No, not this step, the later this particular step in all generality. A of is, and that can be written as, because you know that this you have already seen that A of A e sigma 1 etc. A e sigma n is actually determinant of A into A. Therefore, we make use of that. So you get this is equal to summation over determinant of A to A of A. Now that of course you can pull out determinant of A, which is a constant. That is equal to determinant of A. I pull down summation over sigma psi A of sigma 1 this is something which you can easily. Now that is essential, and this part would turn out to be, if you put this inside again, okay, and then work with it to get this as determinant into so this is something that you can prove for all x1, x2, etc., xn belonging to R. Now, one easy way to understand this, and this for the sake of students, is just run through the calculation for the case n equal to 2 and 3 and see that determinant of A essentially comes out in your thumb. Okay. So, exercise. That will be a good exercise. To do that, it will be clear how these ideas will come about. Okay, I think that concludes our mission, namely to give a structural interpretation for the determinant of a square matrix. Thank you very much.